we're going to learn about assigning oxidation states, so I can then go into learning how to balance oxidation-reduction reactions, which are the most important type of reactions. Pretty much every reaction of significance is an oxidation-reduction reaction. Now, before I start explaining how to assign oxidation states, I'm going to make a recommendation to myself, and that is not to learn this right away. To, in fact, learn about atomic theory before I learn about oxidation-reduction reactions. Because for right now, what I'm going to have to do, which is similar to what happened when I was going to learn about solubility, I have to memorize a table because it's impossible for me to understand in my current state of ignorance. So what I should do is learn about atomic theory, because oxidation-reduction reactions, I really need to know about what the ultimate goal of all of these chemical reactions is, and that is to achieve a stable electron configuration. And I also need to learn about electronegativity and what the different priorities there are when there is a chemical reaction taking place. For example, oxygen is usually -2, but so is sulfur. However, in an example I'm going to do shortly when I assign oxidation states, sulfur is going to be bonded to fluorine, which is -1. However, fluorine is more electronegative than sulfur is, so it is going to have greater priority for the electrons. So the -2 oxidation state that sulfur usually has will not be there. It is not going to have a -2 oxidation state. And that is why oxygen is very, very electronegative. But in some cases, it will not be a -2. That is why it says usually. Of course, I would not understand that because I don't know atomic theory at this point, had this been the first time I ever saw this. And once I learn about atomic theory, this table will not need to be memorized. I will already know this table, and I will know a whole lot more. I will know when it is likely that the rules will be bent for this table, when the rules will be extended. I will be able to, I will have a lot more intuition in assigning oxidation states, which is why I recommend not learning this as of right now, waiting until I have learned about atomic theory, orbitals, electronegativity, and only then come back to this. However, this table is quite small, and it's not as egregious as the solubility table, which is completely ludicrous. Here, the only important things to really know are oxygen is usually -2, elements have no charge, monatomic ions have the charge of the ion, and fluorine is -1, which is not seen very often in beginning classes, to be honest. I mean, and it's always going to be -1. I really can't think of any compound where fluorine is not -1, so that's very helpful. And then hydrogen is +1. So there really isn't too much to memorize, which is the only reason I am going over this, because it's not as ludicrous as the solubility table. And that's the thing, the reason atomic or atoms and elements have no charge is because they have equal electronegativity, but of course I would not know that as of right now. So that's why I really recommend, again, I can't really emphasize enough, just go learn atomic theory first, come back to here, and all of this will make perfect sense. Will not need any explanation. But anyways, let me go ahead and start assigning a few oxidation states for some compounds. For example, carbon dioxide. Ugh. Now I want to assign oxidation states to each atom in this compound. Now this compound has a net charge of 0. That's an important thing to notice. So whatever the oxidation states assigned are, their total, the summation of all of the oxidation states in this compound must equal 0. So let me consult my table, and I see that I have oxygen is usually -2, and when will it not be -2? Well, when something is more electronegative, or if it's competing something that is equal in electronegativity to itself, or there are a few other situations. But of course, again, I won't know that right now. So go learn atomic theory. I'll continue to try to convince myself to go ignore this video and go learn atomic theory. But anyways, if I've still ignored my own warnings, I'm going to go to oxygen. It's usually -2. I'm just going to assume as of right now that I'm completely ignorant. I do not know when it will not be -2. So for all intensive purposes, if I don't know atomic theory and I don't know anything else, it's always going to be -2. So I'm going to assign oxygen -2. And there are 2 of them. So in order to make this completely equal to 0, have a neutral charge, carbon must be +4. If I had just assigned it a +2, there are 2 oxygens, and then the total oxidation state would have been -2. So carbon must be +4. Now the oxidation states add up to 0 because there are 2 oxygens. Carbon has an oxidation state of +4. Oxygen has an oxidation state of -2. And that's how oxidation numbers are assigned. I'll do a couple more examples just to get the hang of it. I have sulfur and 6 fluorines. Now here was an example where which I have seen tables in other books where they say sulfur is -2, or usually -2, and it is true, it's perfectly true. But I notice that oxygen is right above sulfur, and the reason that they are both -2 is because they need 2 more electrons to achieve an octet, which is something that I would learn in atomic theory, so I really should go learn atomic theory. But anyways, fluorine is over here. It only needs 1 more electron. It's the most electronegative element on the periodic table. It's really more electronegative than it. So it is going to have, of course, I don't know what that means right now, so I don't know what I'm talking about. But anyways, fluorine is stronger than oxygen and sulfur when it comes to fighting over electrons. So the usual oxidation state of -2 of sulfur is going to be overlooked because of the stronger electronegativity, which I don't know what that means, of fluorine. So anyways, fluorine is always -1. Always, always, always. Actually, I've never heard of it not being -1. So I'm going to assign this a -1, and the overall charge of this is equal to 0. There are 6 fluorines, so sulfur has a oxidation state of +6. And that's how this works. Let me do one more. NO3 minus. Now here's a situation where that looks like a 6 over there. This is a 0. But here's the situation where the charges or the oxidation states do not add up to 0. These need to add up to -1 because it's a minus charge. If it was a -2, then it would need to equal to -2. If it was -3, then that would need to equal -3. Or if it was +1, need to equal +1, and so on. And here I go back to my table and my trusty oxygen, which for all intensive purposes is always going to be equal to -2 for as long as I don't study atomic theory, because I'm not going to know any better, which is why this is kind of silly. So then anyways, -2, there are 3 oxygens. I need to be equal to -1. 3 times -2 is -6. So therefore nitrogen must be plus 5. And it's good to know, it's good to check and always add up the oxidation states in the beginning, because sometimes it's very easy to make a careless mistake and just say, oh, nitrogen plus 6, but it's an ion, it has a minus charge, so it needs to be equal to minus 1. 3 times minus 2 is minus 6, plus 5, minus 6, minus 1. So that's oxidation states, and what this is going to lead into, which I will probably talk about, I guess I'll talk about it now, is oxidation-reduction reactions, how to classify an oxidation-reduction reaction. Now, a very simple one, and a lot of times they can get a lot more complicated. It's like metabolism, sugar, all kinds of stuff, burning something, and just all those are oxidation-reduction reactions. But here's a very simple one. Here I have solid sodium reacting with chlorine gas, giving me sodium chloride crystals. Now, what makes this an oxidation-reduction reaction exactly? Well, if I go back to my table, I know, the thing for oxidation-reduction reactions is to go around assigning everything in oxidation state. So I'm going to assign everything in oxidation state on this left-hand side first, and I'll explain it like that. Atoms that are in elements have oxidation states of 0, and that's because they are the same as each other. So one cannot pull an electron away from the other one because they're of equal strength, like a tug of war with two people of equal strength. So these are elements on this side. This is just sodium, this is just chlorine. So this sodium is going to have an oxidation state of 0. These chlorines are going to have an oxidation state of 0. Now they react, and it becomes sodium chloride, and the net charge on that is 0. However, in compounds, well, I don't know why this chart didn't have chlorine. Anyways, pretty much everything, I guess I'm already going into a little bit about atomic theory. Pretty much everything in this row right here, fluorine, chlorine, bromine, iodine, and I don't even know what that atom is, but pretty much every element in this last row, these are called halogens, and they need one electron to achieve a stable octet or electron configuration. Everything in this row is pretty much going to be -1. The electronegativity decreases when it goes down, but usually the more common ones for right now are going to be fluorine and chlorine. And especially right now, where I'm in a position of complete and total ignorance because I don't know anything about atomic theory, fluorine and chlorine are essentially always going to be -1. I don't know why they didn't include that in the table and then give me a question like that. It's pretty ridiculous. Oh well. Never really expected any genius ideas from these book publishers. Whatever. But anyways, I'm supposed to know that chlorine is -1, which really goes back to I really need to go study atomic theory. Chlorine is -1 as an oxidation state, so therefore that makes sodium +1. Of course, I would not have known that according to this table, even though they gave me questions that I don't know the answer to because I haven't studied atomic theory, and whatever, it's stupid. But anyways, this would be how to assign oxidation states for a reaction. And now what I'm going to do, or what I should notice, is that the oxidation state changes. Sodium goes from an oxidation state of 0 to +1. Chlorine goes from an oxidation state of 0 to -1. And this is what defines an oxidation-reduction reaction. It's when electrons are transferred from one atom to another. So here I'm going from 0 to 1. This is called oxidation. Here I'm going from a charge of 0 to -1. This is called reduction. And the reason it's called oxidation is because oxygen is one of the best atoms, or elements, I should say, one of the best elements at stripping away electrons from others, because it's very, very electronegative. And of course, we'll not know that unless we study atomic theory. But that's why they call it oxidation, because oxygen's very good at it. But of course, I think the only one that's probably better at it is fluorine. I think fluorine is definitely more electronegative than oxygen. I don't know if chlorine is, probably, but it would be close. But anyways, when our charge goes from, doesn't necessarily have to be 0, it could already be a positive charge, but when something increases in charge positively, it's called oxidation. When something decreases in charge, it's said to undergo reduction. And that's really the definition of an oxidation-reduction reaction, when I have oxidation states changing from the reactants to the products. And then I'm going to go in more detail about this, because usually they're not just this simple. Sometimes balancing them can be a little bit of a challenge, and I'll be going into that over the next video or two. But go study atomic theory.